This is part 2 of the series Limits, and in this part we're going to talk about where limits fail to exist. In the last part we discussed limits, finding limits numerically, and there are three primary and a secondary condition, a fourth condition, where limits fail to exist. So let's take a look at each one of these in their turn and see if we can make sense of this. The first condition, we're going to use the absolute value of x divided by x, and we're going to take the limit as x approaches 0. You can see that the behavior of this function on the left, the function is always equal to negative 1 on the left of 0, and it's always equal to 1 on the right of 0. So the behavior from the left is different from the behavior from the right, which means this function does not converge on any specific value from the left and from the right. And that's a requirement for limits to exist. So we would say that this limit does not exist. And it's generally appropriate to denote this as does not exist, or DNE for short. I usually abbreviated DNE, does not exist. So this is different behavior from the left than from the right. This is going to become important when we discuss the fourth one as well. So let's take a look at the second condition. For this condition, we're going to use the function 1 over x squared, and we're going to take again the limit as x approaches 0. Now if we look at the behavior of this function from the left here, it's increasing without bound, and here it's increasing without bound. So again, this function is not approaching any real number. It's increasing without bound on the left and the right. Now there is debate out there as to what is appropriate to write in response to the question, what is the limit as x approaches 0 of this function? And you will sometimes see certain authors that will say something like this, equals infinity. Because from the left this function is approaching positive infinity, and from the right it's approaching positive infinity, they would say that the limit equals infinity. Make sure you understand this is not saying that the limit exists. This is actually telling you why the limit doesn't exist. This is telling you that the function has unbounded behavior. It's approaching a non-real value. It's not approaching a real value. Therefore, you must say the limit does not exist. Therefore, the limit does not exist. I always instruct, if you're going to say this, you must say this, but it's also appropriate just to say the limit does not exist. In either case, it's important to understand that the statement equals infinity is not saying it's equal to some number, because infinity isn't a number. It's a concept. And so this limit does not exist. Let's take a look at the third primary reason. The third condition where limits fail to exist is where we have oscillating behavior. That is, the function is oscillating between two values, or more than one value I should say, and it never settles. Just like here it doesn't settle on one number, or here it doesn't settle on a real number, this never settles on a specific value. And characteristically, we're going to use this function is often used to describe oscillating behavior, the sine of 1 over x. Before we get into the limit itself, let's spend a little time and analyze this function and see why this function is oscillating. And then that'll give us a greater insight into why this limit doesn't exist. So we're going to take a look at this function. So here we have this function, sine of 1 over x, and we're using an interval from 0 to about pi, 3.1-ish, and you can see that the function isn't even going through one oscillation between 1 and 2. You can see that it's just kind of decreasing here, and the same thing on this side. But as we get closer and closer to 0, you can see that the function is oscillating more and more times. Let's see if we can investigate why that is. Well, if the x value is 1 and we put 1 into this function for x, we have sine of 1. Well, 1 over 1 is just 1, and 1 over 2 is 1/2. So what we have is a distance from here to here on the x-axis for sine to travel 1/2 a unit, or 1/2 radian. Now let's take a look at the interval as we go closer in. Let's look at it on this side. Let's move this out a bit, and let's look at it from point 1 to point 2. You can see that the function is oscillating a little bit more. Let's pull up a calculator and see if we can't figure out what this interval is for sine. So we have 1 over 0.2, 1 divided by 0.2 is 5. So 1 over 0.2 is 5, so we'd be taking the sine of 5, and the 1 over 0.1 is 10. So the interval on the x-axis, as far as sine is concerned, is 10 units from here to here, because 1 over 0.1 is 10, and 1 over 0.2 is 5. So there's 5 units in between here. So that means sine we have to go from the sine of 5 to the sine of 10. That's quite a few oscillations of 2 pi, which is the period of sine. Now let's go one step further. Let's go in even further here. And let's move this in to 0.01 and 0.02. Let's keep going. And here we have 0.01 in here and 0.02 here. We can see the oscillations are increasing fairly dramatically. So let's bring up our calculator again, and let's do 1 divided by 0.02, which is 50, and 1 divided by 0.01, which is 100. We've increased tenfold. Here we had an interval of 5 units. Here we have an interval of 50. So between here and here, we're evaluating sine at the values of sine of 50 to the sine of 100. That's 50 to 100. That's quite a few cycles of sine, quite a few cycles of 2 pi. So now going back to our calculator, if we take 5 units divided by 2 pi, we get 0.79, and if we get 50 divided by 2 pi, we get 7.9. So we've increased the number of cycles by a factor of 10. So here we went through one cycle, or less than one cycle. Here we went through almost 8 cycles. And as you can see, if we went in to 0.001 to 0.002, we'd increase by another factor of 10, which would be a factor of 1,000 from the original, and we would go through almost 80 cycles of pi. So that's why this function is oscillating. Its sine is going through more and more cycles of 2 pi as we get closer and closer to 0, because the interval is increasing that we're inputting into sine. So let's go back to our original drawing, and we would say, because this function is not settling on a real number, any particular real number, it's oscillating between -1 and 1. As we get closer and closer to 0, it's oscillating more and more times. We must say that the limit as x approaches 0 of this function does not exist. Now the fourth condition is related to the first up here, and that is if you had a function that was being evaluated on a closed interval. So let's say we had some function like this, and we wanted to find out, let's say that this is some a value and this is some b value, and we wanted to find out what's the limit of this function as x approaches a of f of x. Well, since this is a closed interval, we can only approach a from the right, because the function doesn't exist to the left. So we can't approach this function from the left, so there's no way to evaluate the behavior from the left. So whenever we're evaluating a function, the limit of a function on a closed interval, and specifically trying to find the limit of a function at the endpoint of a closed interval, we are going to be forced to say that this limit does not exist. And we'll get more into that when we talk about one-sided limits, but that's the fourth subcategory where limits fail to exist. All right, well, let's move forward and let's look at the formal definition of a limit. What I'm going to do first is read the formal definition, and then we're going to try and step through it one piece at a time to see if we can make sense of this. So the definition says, let f be a function defined in an open interval containing c, except possibly at c, and let L be a real number. The statement, the limit as x approaches c of f of x equals L, means that for each epsilon value that's greater than 0, there is a delta value greater than 0, such that if x minus c is between 0 and delta, then f of x minus L is less than epsilon. Now let's see what all this means. Let's break this down. First, let's take a look at this idea of open interval. This relates back to our previous example where we talked about behavior of the function from the left and from the right. An open interval allows us always to approach any value from the left and from the right. No matter how close you get to an endpoint, if it's an open interval, there's always one value to the left and one value to the right that allows us to get in there. So that's what this open interval means. And containing c means there's some c value where the function is either defined or undefined, but the interval that we're evaluating this limit across contains that c value. And this except possibly at c means the function doesn't necessarily have to be defined at c. In fact, that's at the heart of the concept of limit, because in limits we're not dealing with what the function is at that c value. We're dealing with what the function is approaching at that c value. And L being a real number, c and L both being real numbers. And this statement means that there's an epsilon value. The distance between some f of x and the limit value itself is your epsilon. So this distance is epsilon, this distance is epsilon. There has to be a delta, a positive delta value. If you have some value x and it's either here or here, and you take the absolute value of x minus c, this distance is your delta, this distance is your delta. So that x minus c is going to be your delta distance. And so this is stating that if there is a positive epsilon distance, then there must be a positive delta distance such that your absolute value of x minus c, the absolute value of x minus c, has to be greater than 0 and less than delta. So any x value is in this region, then the f of x minus your limit is going to have to be within your epsilon. So again, if there's a positive epsilon, then there must be a positive delta such that x minus c, such that if x minus c is between 0 and delta, then there has to be an f of x minus L that's less than epsilon. And that's all this definition is saying. And it seems like a convoluted way to say a fairly simple thing, but it's necessary to have that level of rigor to handle all the necessary cases. Now in the next part, we're going to go ahead and use the epsilon delta definition to solve some problems, and then we're going to continue on talking about other issues related to limits. So I will talk to you in the next part.